Hello, I am Minyoung from KAIST. I'm going to introduce our paper titled The Classification of Edge-Dependent Labels of Nodes in Hypergraphs. Group interactions are prevalent in various aspects of our lives. For instance, research papers typically involve a collaboration among a group of researchers, and emails are frequently addressed to multiple recipients. Hypergraphs offer a natural representation for studying group interactions, surpassing the limitations of pairwise graphs. For instance, in co-authorship datasets, each publication can be viewed as a hyperedge, with authors represented as nodes within it. However, in many real-world hypergraphs, node properties can vary based on the hyperedges they are involved in. Let's consider co-authorship as an example. In this scenario, the same researcher can have different labels such as first author, last author, or others, depending on the specific publications they are involved in. Hence, we present a novel problem, edge-dependent node classification in hypergraphs. The problem is formulated as follows. When a hypergraph, a set of edge-dependent node labels, and optionally a node feature matrix are given, the problem is to accurately predict the unknown edge-dependent node labels. To illustrate this problem, let's consider the co-authorship dataset mentioned in the introduction. In this dataset, edge-dependent node labels are assigned based on the position of authors within each publication. For example, author YB may be labeled as the first author in one hyperedge E1 and as the last author in other hyperedges. Furthermore, our problem extends to online Q&A platforms. In this context, each hyperedge represents a post, and the nodes within the hyperedge correspond to the users contributing to that post. Users can be labeled differently based on their roles, such as being the questioner, the answerer chosen by the questioner, or one of the other answerers. Additionally, the problem can be observed in the context of emails. Here, each email can be represented as a hyperedge, and the individuals involved in the email are represented as nodes within that hyperedge. Individuals can be classified based on their roles, such as being the sender of the email, listed in the CC field, or designated as the receiver of the email. We introduced WHATSNet, a network designed for edge-dependent node classification in hypergraphs. Its key focus is to address the challenge of capturing node variations across hyperedges through the generation of hyperedge-dependent node embeddings. This is achieved by adapting input embeddings using WithinATT, an attention model that incorporates the WithinOrderPE positional encodings. As a motivation of the attention model WithinATT and WhatSnet, we consider the following example. If a grown-up researcher co-authors a paper only with students, she is likely to be the last author of the paper. Conversely, if she co-authors with other grown-up researchers, then the probability of her being the last author of that paper is relatively low. Thus, we observe the fact that the node label is shaped by the other nodes within the same hyperedge. Motivated by this observation, we devise within ATT based on transformer, and it adapts a node embedding by attending to the other nodes in the same hyperedge. Specifically, within ATT utilizes a set of node embeddings as queries, keys, and values within each hyperedge in the attention mechanism. For example, in hyperedge 1, the edge-dependent node embedding of node 2 is influenced by node 1 and 4. However, in hyperedge 2, it is influenced by node 3, 4, and 5. As a result, although the input embedding of node 2 is the same for both hyperedge 1 and 2, their edge-dependent node embeddings are different. WithinOrderPE is a positional encoding technique that takes into account the relative positions of nodes within each hyperedge. It leverages centrality metrics to capture the importance of nodes compared to others within the same hyperedge. For example, in co-authorship datasets, the degree centrality reflects the number of papers authored by each researcher. So the author with highest centrality is often the best author. To illustrate the computation of a WithinOrderPE, let's consider an example involving three types of node centralities. In hyperedge 1, which consists of nodes 1, 2, and 3, node 2 has the smallest value in the second centrality measure. Node 3 is the second, and the node 1 is the third. Each type of node centrality corresponds to each dimension of WithinOrderPE. So the second dimension of WithinOrderPE within the hyperedge 1 is computed based on this order of the nodes divided by the size of hyperedge 1. Similarly, in hyperedge 2, which includes nodes 3 and 4, node 4 has the smallest value, and the node 3 has the second smallest value in the first centrality measure. Consequently, the first dimension of WithinOrderPE in hyperedge 2 is computed accordingly. Our final model, WHATSNet, integrates WithinATT and WithinOrderPE. First, WithinOrderPE is incorporated into the node embeddings within each hyperedge. WithinATT is applied to generate hyperedge-dependent node embeddings. Then they are subsequently aggregated to update the hyperedge embeddings. WhatSnet updates both node and hyperedge embeddings by 2 steps, and each update step is the same as we described before. In the first update step, the hyperedge embeddings are updated using the node embeddings within them. When the hyperedge embeddings are all updated, the node embeddings are subsequently updated based on the embeddings of the incident hyperedges. Once the node and hyperedge embeddings have been updated iteratively, we proceed to predict the edge-dependent node labels using a single-layer perceptual classifier. This classifier takes as input the concatenated node and hyperedge embeddings obtained from the last layer of WhatSnet. In our experimental analysis, we utilized 6 real-world data sets spanning 3 domains: co-authorship, email, and online Q&A platforms. We evaluate the performance of WHATSNet against 8 baseline approaches of hypergraph neural networks. Additionally, we apply WhatSnet to 3 specific applications where edge-dependent node labels play a crucial role. To assess the accuracy of predicting edge-dependent labels of nodes, we evaluate the performance of WhatSnet using micro F1 and macro F1 scores. Across all 6 datasets, WhatSnet consistently outperforms 10 competing models in terms of both metrics. To analyze the ability of WhatSnet to classify nodes differently depending on hyperedges, we examine the node-level label distribution. This distribution represents how frequently each node is assigned a particular label. By measuring the Jensen-Shannon divergence between the predicted and ground truth label distributions, we assess the accuracy of WhatSnet in preserving the true node-level label distributions. In comparison to competing models, WhatSnet exhibits the smallest distance, indicating that it effectively preserves the ground truth node-level label distributions. We analyze the contribution of each component in WhatSnet to its performance, comparing the variance without WithinATT and without WithinOrderPE. We found that the variant without WithinATT performs worse than the variant without WithinOrderPE and the full WhatSnet model, which highlights the crucial role of WithinATT. Similarly, the variant without WithinOrderPE is outperformed by the full WhatSnet model, which demonstrates the significance of WithinOrderPE. In summary, both the WithinATT and WithinOrderPE components play integral roles in enhancing the performance of WhatSnet. Finally, we evaluate the practical usefulness of WhatSnet in real-world downstream tasks. We consider 3 downstream tasks and compare their performance using different approaches. Ground truth edge-dependent node labels, labels predicted by WhatSnet, and no labels. In the first task, the ranking aggregation task, the goal is to accurately predict the global node length using the local node length within subsets. For instance, in a multiplayer game scenario, players are represented as nodes, and subsets of players participate in matches where they receive scores. These scores serve as edge-dependent labels. The task involves predicting the ranking levels of players among all players based on the match results. We compare the performance of the task when using ground truth edge-dependent node labels predicted by WhatSnet or no labels. We assess which case yields the best performance for accurate prediction. In the next task, clustering, the objective is to group subsets that share similar properties. For instance, in co-authorship dataset, those represent authors, and each hyperedge represents a publication. The edge-dependent labels in this case represent the order of co-authors within each publication. We compare the performance of clustering publications with the same venue using different types of edge-dependent labels to determine which approach leads to better results. Lastly, we consider the product return prediction task, where the goal is to predict the likelihood of the products being returned for each cart. In this task, cards are represented as nodes, and items are hyperedges. The count of an item in each cart serves as the edge-dependent labels. Multiple purchases of the same product within a cart may indicate variations such as different colors or sizes, so increases the likelihood of product return. Thus, using these edge-dependent labels, we aim to predict the probability of products being returned for each cart. We compare the performance of this task when using three different given edge-dependent labels to determine which approach produces the most accurate predictions. Consequently, across all three downstream tasks, utilization of edge-dependent node labels predicted by WHATSNet consistently leads to performance improvements compared to the results obtained without labels. As a conclusion, our contributions are summarized as follows. First, we formulate a novel problem of the classification of edge-dependent labels of nodes in hypergraphs. Second, we propose What'sNet, a comprehensive model that incorporates the WithinATT and WithinOrderPE. Lastly, we demonstrate the superiority of What'sNet compared to 10 competing models and show its practical usefulness in three downstream tasks. The code and data sets used in the paper are publicly available at the given link. Thank you for listening to my presentation.